Hello everyone, welcome to week 8 problem solving session for the pattern recognition and application course. As you know, I am Tanuka from IISc Bangalore. So in today's session we are going to solve some problems on perceptron criteria, MSE criteria, Kessler's construction and similar things that you have learned in this week's lecture. So let us get started with our first problem for today's session. So for this one I would like any one of you to answer. So the question is, in perceptron criteria, which of these expressions is correct for sequential update of weight vector? So since this is the basic the fundamental formula for perceptron criteria, so yeah, the answer is option A. So you have to in the k plus 1th iteration, your solution vector A is given by ak plus eta times yk. So here we are considering this eta is basically the learning rate, and in yk we are considering that these are augmented feature vectors. So we have appended one at the end of the original feature vector, and also we have multiplied it by minus 1 for class omega 2. If we are considering two classes, then for one class we are considering the original feature vectors, and in the other class we have multiplied them by minus 1. Okay. So this is the original this is the actual way update rule for perceptron criteria. Now moving on, the next question is, in perceptron criteria, sequential update of weight vector, what is its significance? So does it require more memory space than taking all samples together, or less memory space, or same memory space, or we cannot comment? What is the scenario? Again, can any of you answer this? So sequential update of weight vector means at each iteration you are taking one feature vector from your training data set, you are checking whether that one is getting correctly classified or not, and you are correspondingly updating your weight vector or your solution. So you are not taking all samples together. So when you are considering all samples together, you will have to take this summation over yk for all y which are misclassified. But here you are not taking that, you are just considering one sample at a time. So of course this will require less memory space, because you don't need to have all the samples and sum all the misclassified ones up. Not like that, you just take one sample at a time and you classify that, and based on that you update the solution vector or weight vector. So you need much less memory space as compared to taking all the samples together. So that is basically the motivation for going into sequential update of weight vectors. Now the next question is, which of the following statement is true for perceptron criteria? Whether the convergence is always guaranteed, or it is guaranteed for linearly separable classes, or both or none. What is the scenario? So as you will know that perceptron criteria, for the matter of fact also relaxation criteria, both are, the convergence is guaranteed for both of these when the data we have are linearly separable, or the classes that we are having in the training set, those are linearly separable. In that case, these algorithms have guaranteed convergence. So you will definitely end up with a solution vector that can perfectly classify your entire training data. So, the option B is here the correct answer. But let us have a look on how we are stating that the convergence is guaranteed for linearly separable classes, but we should prove that. So, let us see how we can prove that when you have linearly separable classes and you use perceptron criteria to determine your classifier, then of course you will end up with a linear classifier, which can definitely classify your training set. So, let us try to prove this statement. So, for that let us say we are considering augmented feature vectors. First of all, we are considering augmented feature vectors. So, if you have augmented feature vectors, let us say we denote those by xi, I equals to 1, 2, 3, like that you will go. These are the augmented feature vectors. Just a minute. Yeah. These are the augmented feature vectors xi that you are taking, and let us say they belong to two different classes. Okay. Now, so let us say w is your weight vector. So, when you are the original expression for your discriminant function would have been w transpose xi plus w naught, right. You will see whether this is positive or negative or equal to 0. Based on that you will do the classification. But here, since we are considering augmented feature vectors, we have appended 1 at the end of xi, each xi, and we have considered this w naught appended at the end of w. So, now you have the augmented weight vector as well as the augmented feature vector. So, that we can as a whole write as w transpose xi. You do not need to specify w naught separately. W naught is already within this vector w. The last element of this vector w is basically the bias term w naught. To include that, you have appended 1 at the end of all xi, right. So, this becomes w transpose xi becomes your discriminant function. Okay. So, if this w transpose xi is greater than 0, then you say that let us say xi belongs to class omega 1, and if it is less than 0, you say that your xi belongs to class omega 2 and it is equal to 0, then you say that xi is on the decision boundary. Right. So, this is the situation you have. Now, let us say in your training data you have two classes omega 1 and omega 2. Let us say you multiply all samples coming from class omega 2 by minus 1. So, in that case, here you had the condition that w transpose xi should be less than 0 for the xi belonging to omega 2. Now that you have multiplied every xi of class omega 2 by minus 1, so automatically this product, this inequality will change. So, now for class omega 2 also you will get w transpose xi greater than 0. So, originally you had w transpose xi less than 0. Now, you have multiplied xi by minus 1, all elements of it by minus 1. So, now your w transpose xi has become greater than 0. So, now the situation is, so you multiply all xi element of omega 2 by minus 1. So, by that I mean you multiply each element of the vector xi by minus 1. Okay. So, if that you do, then the situation becomes w transpose xi will be greater than 0, but that means xi is correctly classified, right. and else you will have less than equal to 0 otherwise. So, both classes when they are correctly classified, that will lead to W transpose Xi greater than 0. So, since you have multiplied by the negative sign, so you do not have that greater than less than business anymore. So, now our scenario is we have these Xi's which are augmented feature vectors as well as the ones belonging to class omega 2 are multiplied by -1. So, if we have to find the W vector such that W transpose Xi is greater than 0 for all Xi. Okay. And we will try to solve this according to the perceptron criteria. We will try to obtain W following the perceptron criteria. So, what is the sequential perceptron algorithm in this case? So, sequential, I am taking the sequential algorithm here. So, perceptron algorithm will be your Wk plus 1 will be equals to Wk plus eta times Xk, right. If your Wk transpose Xk is less than equal to 0. So, you make this update only if you have a sample misclassified, right. Then only you take that sample and add it to the previous iterations weight vector. So, whenever, since now you have modified these Xi's such that whenever you correctly classify a sample, it will lead to W transpose Xi becoming positive. So, whenever you are getting less than equal to 0, that means you have misclassified that particular sample. So, whenever you are getting less than equal to 0, then you will have to update your weight vector following this formula, Wk plus 1 equal to Wk plus eta times Xk. Okay. And here we can also consider that we will count this number of iteration k only when the W is updated. In that case, we will have k equal to 0, 1, 2 like that. So, otherwise you in some iterations you may not update the weight vector because you are getting correctly classified sample. So, in that iteration by the rule you will not update the weight vector. So, we are not counting those in the k index, we are just counting the iterations whenever the weight is getting updated. So, our k will be from 0, 1, 2 like that. It will go on. Okay. Now, so we have to show the convergence, that it surely converges when you have linearly separable classes. So, when does this algorithm converge? When it is correctly classifying all the samples, when it has found the separating hyperplane, then it stops, right. So, it is correctly classifying all your training samples, it has found the linear hyperplane, separating hyperplane, so it has stopped. So, in our case, so it has stopped means that convergence has been achieved. So, in this proof we will go by contradiction. So, let us say that convergence won't be achieved even if you have linearly separable classes. Okay. Let us say convergence won't be, we assume that convergence won't be achieved. Okay. So, in that case the algorithm won't be able to find the separating hyperplane, that is it fails to find the separating hyperplane, and if it fails to do so, so always if it is not being able to find the hyperplane, the separating hyperplane, then the thing is it will always keep on misclassifying some sample and it will always keep on updating. So, the iterations will keep on going, you will not stop. So, when you stop, then all the samples are correctly classified, but here your convergence is not achieved, you are not stopping. So, continuously you are making some mistake and you are keeping on updating the weight vector. So, your since we are assuming that convergence won't be achieved, so your algorithm won't stop. Now, if your algorithm doesn't stop, that means at each iteration you have to find wk transpose xk less than 0 for all k. So, you will have to keep on finding, you will continuously will get samples which are getting misclassified. Each iteration you will get one sample that is getting misclassified. So, all are not getting correctly classified ever. Okay. So, this is our condition by the contradiction assumption. Contradiction assumption that convergence won't be achieved. Okay. So, this is your condition. Now, so for simplicity, let me take eta equal to 1 for this case. This is like you can take any value of eta. I am taking eta equal to 1. So, your weight update rule is wk plus 1 equals to wk plus xk. Right. This is your weight update rule. Now, let us take the norm square on both sides. We are taking the norm square on both sides. Now, if you expand the norm square on the right side, that is norm of wk plus xk square, if you expand that, what you will get is norm of wk square plus norm of xk square plus twice wk transpose xk. This is what you will get. Now, we are saying that since convergence won't be achieved, at each k we will have wk transpose xk less than 0. Right? So, this is the condition we have, wk transpose xk less than equal to 0. So, that means this term is always less than equal to 0. If that is the case, then if that is a negative term, then we can write wk plus 1 norm square will be less than or equal to wk norm square plus xk norm square. Since the last term wk transpose xk is always negative. Okay. So, the right hand side wk norm square plus xk norm square is greater than or equal to wk plus 1 norm square. Okay. Now, if you recursively put this expression in wk, so what you will get is, so norm of wk square will be less than equal to norm of wk minus 1 square plus xk minus 1 norm square. Right? Yeah. Now, you can similarly expand wk minus 1 norm square. So, you will get wk minus 1 norm square will again be less than equal to the sum of norm of wk minus 2 square and xk minus 2 norm square. Right? So, you can expand it that way. So, you will get this. You will get this norm of wk minus 2 square plus norm of xk minus 2 square plus norm of xk minus 1 square. This way you can keep on putting the values of W, keep on putting this expansion, this inequality for the W, and finally you will reach at W0, which is your initial W, plus you will have all these x terms. So, I am writing that as summation of norm of, let us say, I denote this by I. So, norm of xi square, where I will be from 0 to k minus 1, right. So, this will be your final form, norm of W0 square plus summation of norm of xi square, summation is over I equal to 0 to k minus 1. Now, here we are again without loss of generality, we are assuming that W0 equal to 0. Let W0 equal to 0, and let us denote the max over I norm of xi square equal to m. The maximum of the norm square of xi, let us say, that is m, and W0 we are assuming as 0. So, W0 we can simply put 0. So, we just have the summation term in this expression. So, in this summation term you have xi norm square for all I. Now, the maximum value of this term within the summation can be m. So, if instead of each norm xi square, if you put m, you will increase the right hand side, because your value will be either less than or equal to m. So, if you put m for all of those, you will either keep same your value or you will increase. So, you can write this as, if you replace all norm of xi square by m, so you will get that norm of wk square is less than equal to k times m, right. K times m. So, this is one expression we got, one condition we got on wk. Let us keep this in mind, we will use it later. Now, let us see another angle. So, you have your wk equals to wk minus 1 plus xk minus 1. This also you can put the expression for wk minus 1, then k minus 2, and keep on putting the expressions in a recursive manner. So, if you put similarly wk equal to wk minus 1 plus xk minus 1. So, your wk minus 1 again will be wk minus 2 plus xk minus 2. So, you can simply put that here. And you can keep on doing this recursive substitution till you get W0 again. So, finally, you will get W0 plus summation of all the x terms from I equal to 0 to k minus 1, right. This is what you will get. Again, we have already assumed W0 equal to 0. So, this becomes simply the summation term, or wk equal to simply the summation of xi from I equal to 0 to k minus 1. So, basically your W is a linear combination of the feature vectors that you have. Okay. So, this is one expression again you got. Now, since your two classes in the training data set are linearly separable, since data is linearly separable, there will exist some W star such that if you take W star transpose W star transpose xi, that will be greater than 0 for all I. Okay. That will be greater than 0, because if you know that the data is linearly separable, then there exists some separating hyperplane. So, some W star is there which can correctly classify all these data. So, there will be some W star such that if you take W star transpose xi, that will be greater than 0 for all xi, or you can write it in the opposite also, xi transpose W star, that will be greater than 0 for all I. This is the same, W star transpose xi and xi transpose W star, both are the same. So, since you know the data is linearly separable, so there will exist some W star such that this condition is satisfied. So, this xi transpose W star is always positive. Now, let us say we denote the minimum of this value, minimum over I xi transpose W star, that we denote by gamma. So, your xi transpose W star is always greater than equal to 0. So, your gamma is also always xi transpose W star is greater than 0 always. So, gamma is also greater than 0. Now, being said that if you take xk transpose W star at any iteration k, then what we saw in the previous calculation, xk is basically the sum of all the feature vectors. So, if you put that here, you will get sum of xi transpose W star for I equal to 0 to k minus 1. This will be your expression. Now, the minimum value of xi transpose W star is gamma. So, if you put that, if you consider that minimum value and sum it over I equal to 0 to k minus 1, that is you get k times gamma. So, that will be less than this expression, this summation of xi transpose W star. Since you are putting the minimum value, what you will get is less than this. So, this will be greater than k times gamma. This will be greater than k times gamma, and again your gamma is always positive. So, your k gamma will also be positive. Okay. So, now if you take, so you have, let me write it on a new slide. So, you have k gamma less than equal to wk transpose W star. Now, if you take square, so k square gamma square will be less than equals to mod of wk transpose W star square. Now, this mod square, you can write that it is less than equal to norm of wk square into norm of W star square, right. This is according to the Cauchy-Schwarz inequality or CS inequality, the well known inequality in linear algebra, Cauchy-Schwarz inequality, that we are applying to get that the mod square will be less than equal to individual norm squares product. Okay. Now, we have already determined this expression for wk norm square. Let us see that. So, we have wk norm square is less than equal to km. Wk norm square is less than or equal to km. So, the first term is less than or equal to km. We put km there. And let us have this. Okay. So, initially what we said that if convergence is not achieved, in that case your iterations will keep on going. You will keep on updating your weight vector, and by assuming that condition we have achieved, reached here. So, this is the condition that we have when you do not have convergence. So, this condition should be valid for all k, since the algorithm will keep on updating. So, this condition should be valid for all k. But here you can easily see that k, this expression implies that k is less than or equal to m w star norm square by gamma square, right. So, your k is less than equal to a finite value. So, this condition is valid up to some finite k value. So, it is not infinitely for all k, this is not valid. So, the assumption that we made that convergence won't be achieved even if we have linearly separable class, that is not true. That means, if we have linearly separable class, then convergence will certainly be achieved in some finite number of iterations. So, convergence is guaranteed. So, here we have assumed the step size as 1, but it is also applicable to any step size you take. This convergence is guaranteed if you have linearly separable classes. And we use the approach of proof by contradiction to prove this convergence. Okay. If anyone has any doubt, you can put it up. Otherwise, I will move on to the next problem. I hope this is clear to everyone, that how you can show that the convergence is of course guaranteed for perceptron criteria if you have linearly separable classes. Okay, so let us move on. Move on to the next problem, problem 4. So, it says consider two class classification problems with 2D Boolean feature vectors. Boolean feature vector means it can assume only the value 0 or 1. Each feature can assume the value 0 or 1, and like that you have 2D feature vectors, and you are considering two class classification problem. Two class classification problem and 2D Boolean feature vectors. Now, we are given two specific classification tasks. What is the first task? A feature vector should be in class 1 if the integer represented by it is divisible by 2, otherwise it should be in class 2. So, if you have a 2D Boolean feature vector, you can have only finite number of combinations, right? Particularly, you can have 4 different feature vectors. So, you can have either 0 0 or 0 1 or 1 0 or 1 1, right? Now, it is said that if the integer represented by this feature vector is divisible by 2, then it is in class 1, and if it otherwise it is in class 2. So, you have this one, this represents integer 0. So, this is element of class 1, or let us say we write that as omega 1. This integer value is 1, 0 1 is integer value is 1. So, it is not divisible by 2. So, it will belong to class 2. Now, 1 0, the integer represented by this is 2. So, it is divisible by 2, it will again belong to class omega 1. And finally, 1 1, which is 3. that is again not divisible by 2. So, it will belong to class omega 2. Okay. And there is one more condition given, but the question is, in each of these cases, here in each of these cases, state whether the perceptron criteria is suitable for designing the classifier. By looking at this distribution, you will have to say whether the perceptron criteria is suitable for designing your classifier. So, we know when we can apply perceptron criteria with guarantee that we will definitely get the separating hyperplane when we have linearly separable classes. So, we have to check by these feature vectors that whether the classes that we have here are linearly separable or not, right. So, to see that, let us plot these feature vectors. Let us say I will put the first dimension along the horizontal axis and the second dimension along the vertical axis. I am denoting these by x1 and x2. And let us say I will denote the elements of class omega 1 with circle and omega 2 with cross. So, 0 0, which is over here, this belongs to class omega 1. So, this is one sample of class omega 1. Now, 0 1 belongs to class omega 2. So, 0 1 belongs to the other class, let us say here. Now, 1 0 again belongs to class omega 1. So, 1 0, which is over here, will be denoted by circle, and 1 1, which is somewhere over here, this is again belongs to class omega 2. So, these are the classes. So, you can surely see that if you have hyperplane or a plane, since this is 2D, this is a straight line, it is not a plane. So, since you are in 2D, the decision boundary will be a straight line. So, if you put any straight line between parallel to x1 axis between these two groups of feature vectors, the crosses and the dots, it will be linearly separating the two classes. So, these two classes you have are linearly separable. So, since these are linearly separable, perceptron criteria is perfectly applicable for this particular situation. Okay. Now, let us see the other situation. In the other situation, number 2, it is said that a feature vector x should be in class 1 if it has odd number of 1s in it, otherwise it is in class 2. Okay. So, again you have these 4 combinations only, If you have odd number of 1s, then you are in, then that feature vector is in class 1. So, here this one is in class 1 and this one is in class 1. The other two, which are not having odd number of 1s, those will be in the class 2. So, now let us plot these also to check for linear separability. So, 0 0 is in class omega 2, 0 1 is in class omega 1, 1 0 is in class omega 1, 1 1 is in class omega 2. So, you see that the diagonally opposite feature vectors are belonging to the same class. So, you cannot draw any straight line that will be able to separate these two classes. So, these two classes that we have are not linearly separable, right. You will have to have some other type of decision boundary in order to be able to separate these two classes. Since these are not linearly separable, as we know, perceptron criteria, the perceptron algorithm won't converge for this type of data set. So, it is not suitable. So, this is not suitable. but the other one that we saw, this one is linearly separable and this is suitable. Okay. Now, the last part of the question says, if it is suitable, then derive the classifier using the perceptron algorithm. So, in this first case where we are having these linearly separable classes, here we have to obtain the classifier, that is basically the weight vector and the bias using the perceptron algorithm. So, let us look into that. So, let us say the feature vectors that you have are 0 0, 0 1, 1 0 and 1 1. Now, you will consider augmented feature vectors, because that is how we have formulated the perceptron criteria. So, we will take augmented feature vectors, that means we will have to append 1 in each of the feature vector. So, we will do that. Now, among these, the alternative ones are in different classes. So, this is in omega 1, this is in omega 2, this is again omega 1, this is again omega 2, right. So, now whichever are belonging to one of the classes, let us say omega 2, whichever are belonging to class omega 2, let us say we multiply those by minus 1. Okay. So, what you will get as the final feature vectors are this, then you have this, then you have this, then you have this. These are the 4 feature vectors that you have. Now, you will have to go through your iteration of the weight vector to finally obtain the final weight vector. So, let us say we assume the initial W as all zeros. Initial W I am assuming all 0. So, let us take the first example, which is 0 0 1. And let us try to classify this using the weight vector, that is we will try to calculate W0 transpose 0 0 1, W0 transpose xi basically, W0 transpose xi. So, since your W0 is all zeros, this will give you 0. So, this is not positive. So, the if your samples are correctly classified, then you should get a positive value, right. Since here you are not getting a positive value, you will have to update W0. And how do you update? So, you will get your W1 as W0 plus eta times your x, let us say the first one is x1, right. So, eta you can take different values. Here let me take eta equal to 0.1. For example, I am taking eta equals to 0.1. So, the W1 that you are getting is basically 0 0 0.1 transpose, right. This is your weight vector after first iteration. Now, you will try to classify the second example using this weight vector and try to see if that is getting classified correctly or not. So, your weight vector now is W1, which is equals to 0 0 0.1, and the second feature vector that you have is 0 minus 1 minus 1. So, you will have to compute 0 0 0.1 and here you have 0 minus 1 minus 1. So, total you will get minus 0.1. Again this is less than 0. So, again this sample is misclassified. So, again you will have to update your weight vector. Now, your W2 will become W1 plus eta times x2. So, your W1 is 0.1 and eta times x2 becomes 0 minus 0.1 minus 0.1. So, your final weight vector is 0 minus 0.1 0. This is your updated weight vector after iteration 2. Now, you will try to classify the next example using this weight vector. So, the third example that you have is 101. So, you will try to compute 0, minus 0.1, 0 and 101, this W transpose X, this inner product, and again you are getting 0. So, the third example is also misclassified. So, you need to update the weight vector again. Now, your W3 will become 0 minus 0.1 0 plus eta times x3, which will be 0.1 0 0.1. So, finally, you will get 0.1 minus 0.1 and 0.1. 0.1 minus 0.1 0.1. Now, you will check the last example, which is the minus 1 minus 1 minus 1. If you take that, that is equal to minus 0.1, right. So, minus 0.1 plus 0.1 minus 0.1, so finally minus 0.1. Again you will have to update. Now, what will your what will be W4? W4 will become 0.1 minus 0.1 0.1, that was W3, plus eta times x4, it is minus 0.1 minus 0.1 minus 0.1. So, finally, you will have 0 minus 0.2 and 0. Okay. This is what you have. So, again you will have to start from the first example. Again take the first example and try to classify using this feature, this weight vector. First example is 0 0 1. So, if you take the inner product 0 0 with 0 0 1 and this vector, again you see you will get 0 because you are multiplying with 0 0 1. So, again you will have to update, and what you will get, since there you have 0 0 1, so here you will get this, right. Here you will get this. Now, take the next example, which is 0 minus 1 minus 1. If you take the product, so you have 0 minus 0.2, sorry, 0.1, and you take it with 0 minus 1 minus 1, you get 0.1. So, you see this is now correctly classified because you have got some positive value of W transpose Xi. So, now for this particular sample you do not need to update your weight vector. You will keep your weight vector same and try to classify the next sample. So, the next sample is 101. So, if you have 101 here, the weight vector is the same, 0 minus 0.2 0.1. Now, you will get again 0.1. So, this is also correctly classified. So, you do not need to update again. Let us check the fourth example, which is all minus 1s. If you have all minus 1s here 0 minus 0.2 0.1, then again you have 0.1. So, this is also correctly classified. Last you will have to check the first sample because you updated last time with that. Now you will have to check with that, which is 001. So if you take 001, write it here. You have 001, you take the product, you again get 0.1. Okay. So for all the samples you are getting positive inner product. So you have achieved at the desired W vector, and this W vector is being able to correctly classify all your samples. So the weight vector that you got is, the W is 0 minus 0.2, that is your original W, with W naught equals to 0.1, right? Yeah. Let us check whether we have obtained it correctly. So the feature vectors that we have are 0 0, 0 1, 1 0, 1 1, right? And these two are in one class, these two are in the other class. So if you now compute W transpose Xi plus W naught, so for the first example, for x1 you will get 0 0, so W transpose is 0 minus 0.2 transpose into 0 0, you will get 0 plus W naught is 0.1. So you are getting 0.1. You classify it to omega 1. Now you take x2. Here you will have 0 minus 0.2 into 0 1. So 0 1, sorry, plus omega plus W naught, which is 0.1. Okay. So finally you are getting minus 0.1. So you classify it in class omega 2. Then you go with x3. So again you are getting 0.1 positive. So you classify in omega 1. And the last one, you are getting minus 0.1 negative. So you classify in class omega 2. So you see, we have correctly obtained a weight vector and a bias term such that all the samples in our training set are getting correctly classified in the two classes. So this is how you proceed through your perceptron iteration or perceptron algorithm to finally converge at a weight vector, which is linearly separating the two classes. Okay. We have arrived at the end of our session today. So we have two more small problems left. The fifth problem is, which of the following is or are true? In perceptron criteria, the probability of misclassification is less compared to relaxation criteria. So as you know, this is not true. So in perceptron criteria, you can have the solution vector or the weight vector anywhere within the possible solution region. So you can have it on the boundary also, which is the feasible solution region. Anywhere within that you can have the solution vector. So it can be on the boundary also. But in case of relaxation criteria, you use a margin term and you further restrict your possible solution area, so that to ensure that your final solution vector is well within that solution possible solution area. So there since you are well within the region, so it's the probability of misclassification is less as compared to perceptron. So in perceptron, the probability of misclassification is more because you can have some boundary at the you can have the solution vector the boundary of the possible solution region. Okay, so this is not true. Next is least square error criteria works well even for non-linear separable classes. So this is, as you know, is true. So when you have non-linearly separable classes, then least square error is the least square error criteria is the best one to go with. Last question is, for a multi-class problem in Kessler's construction, the expression alpha transpose eta ij greater than 0 for all j not equal to I implies which option will it be? So as you know, according to Kessler's construction, when you have alpha transpose eta ij greater than 0 for all j not equal to I, then certainly the sample belongs to class omega I and it does not belong to class omega j. So among class omega I and omega j, we say that the sample belongs to class omega I. So the first option, which is the sample class belongs to omega I, the sample belongs to class omega I is correct, and the sample does not belong to class omega j, that is also correct, because that is the way we are doing this Kessler's construction. When we have alpha transpose eta ij greater than 0, that means the sample belongs to class omega I and not class omega j. So both are correct. So you can say both A and B are correct. So this was it for today's session. If you have any question, you can say that now, or you can write it in the chat as well if needed. Okay, I do not see any questions in the chat box. Then let us close today's session. Thank you everyone for joining. We will meet again in the next week in the next set of problems. Thank you.